So I'm going to talk about mostly something that is exactly what Bob was just talking about in a very different language with basically the same conclusions. And then I thought this was a conference among friends, so at the end I'll actually speculate on some crazy stuff that's not published. So, stay tuned for that. So the title is really kind of a misnomer. It should be something more like comments on checking if the graviton exists, not necessarily directly detecting it. So I've been thinking about this sort of stuff for many years now. I started when I came here in 2014. And this is really one of the reasons I started thinking about it. I read this paper in grad school. Freeman Dyson, who's a hero, asked this very simple question in the title: is a graviton detectable? And specifically what he means is, can I take a gravitational wave detector and scale it or redesign it such that it'll click when a single graviton goes through it? And in a naive reading of the paper, the answer is just no. So I got really depressed, and I thought, well, how am I ever going to know that I should be quantizing gravity? This is, I'm from a high energy theory background, and so if I don't know the graviton exists, like, what are we even talking about in string theory? But then you think a little harder and you actually realize, sorry, there's feedback. Maybe I'll just use do you have feedback? I have feedback here. I'll just stand at the podium. So yeah, you think a little harder about this paper and you realize maybe there's something you can actually do. So let me review the argument briefly, and then I'll talk about ways around it. So the argument is, there's actually two arguments. I want to talk about the one that everyone, including me, remembers because it's the first part of the paper. So Dyson says, I want to take LIGO, and I want to scale it such that it'll click on a single graviton event. So he just treats the graviton sort of classically. He says it just means it's a very small amplitude gravitational wave. And you kind of go through some dimensional analysis. What you work out is, the strain has to be a certain size set by the Planck scale. So roughly speaking, you're going to need to detect position fluctuations at the Planck scale. And if you put in the Heisenberg uncertainty principle, what this means is you're going to have to be detecting a fluctuation with such precision that your measurement device will in fact have to be within its own Schwarzschild radius. So in other words, if you want to build LIGO that can detect a single graviton, the LIGO device itself will become a black hole. So this seems like a pretty good argument that this is not possible. It's a bit hand-wavy, but it's hard to imagine that you're going to really get around this. So you have to think rather hard, what exactly can you break in this argument? I want to talk about two things you can maybe do. Most of the talk will be about these tabletop entanglement experiments like Bob was sort of sketching. So these are, and Marcus talked about the actual experiments. So these are experiments where you do a totally non-relativistic measurement, so it's not naively related to the graviton. Bob gave a very nice argument for why it ought to be. I will give a different argument for the same, which basically says a similar thing. The other thing you could do is try to find a loophole to Dyson's argument directly, and really try to detect individual gravitons. So I'll talk about that a little bit at the end. So these entanglement experiments, this is again the same sort of setup as Bob. I'm just going to talk about this in a sort of high energy language. So the basic experiment is I have two masses. I prepare them in some nice cold quantum states. They talk to each other through the Newton interaction, and what you're trying to measure is whether or not they will become entangled. So this is just a cartoon of how that would go down. You take a mass, you put it in superposition of two locations, you take another mass that talks to it through gravity, and you measure some entangled state at the end of the day. So it's totally obvious in some sense that if the graviton exists in the usual sense of the term, like John was talking about the other day in an effective field theory language, the virtual graviton exchange will lead to an entangling Newton operator, and you'll see the entanglement in the experiment. So what you'd like to claim is the converse, which is that if I do the experiment, I know the graviton has to be there. And as sort of Bob's talk emphasizes, you can't directly say that. You have to sort of put in some other assumptions. For example, the world is causal. You might think that's a mild assumption, but I think the goal is to be very clear what you need to put in. And just to sort of highlight why you should be careful about this. If you just think about gravity in one less space-time dimension, none of this works. So gravity in 3 space-time dimensions has no gravitons. This is an old, ancient result, really, just counting degrees of freedom. There are no propagating degrees of freedom. On the other hand, you can still entangle point masses in it. You just braid them, like in a topological quantum computer or the Aharonov-Bohm effect. So it's a Lorentz invariant field theory, perfectly unitary, well-defined. You can entangle things, and there are no gravitons. So something has to change in 4 dimensions versus just this, sort of barely different model. So I'm going to give an analysis of these type of experiments with scattering amplitudes. So this is the language that Cliff was using. And in fact, this is really a very baby version of the amplitudes program that I had to learn to do this. So instead of thinking about local physics and worrying about the Newton potential, I'm not that smart. I get confused. What's local? What's an observable? Blah blah blah. I'm just going to talk about scattering. So I take 2 masses. I let them interact, I wait for a long time, and then I measure them at the end of the day. So all of these experiments are non-relativistic. They can be described by just the Newton interaction, the 1/r potential. And so then the claim is going to be the following. This is a little formal, but if you take any model and you demand that it comes from a Lorentz invariant, relativistically invariant model, which is unitary, and it can reproduce scattering amplitudes with this Newtonian form, that model has to have gravitational radiation in the asymptotic states. So in other words, it has to include the graviton, in the most naive sense. It can radiate, it exists, and so forth. This is the sort of S-matrix diagram for these experiments. So you'll see this over and over. So these solid lines are the 2 massive particles. I put in the experimentalist Bob and Alice, so they're interacting with something that I'm sort of drawing as photons, lasers, whatever. And then there's some gravitational interaction in the middle. So the rules of scattering amplitudes are pretty simple, actually. So scattering amplitude is an operator that takes time from the far past to the far future. The only baseline rules are that it is unitary. So as an operator, it just S dagger S equals 1. And it's Lorentz invariant. Now I'm going to assume that. That's not always true. But this is, I just put this in to show that you can formulate it mathematically in the usual way. In a little more detail, the way I'm going to use unitarity is what's called the optical theorem. So what you do is you take the S matrix, which is supposed to describe anything that can happen. You write it as a 2-term sum. The first term, this 1, means nothing happens. The particles don't scatter. And this IM means the particles do scatter. And so demanding that this is a unitary operator puts some constraints on the form of this M matrix. And specifically, the imaginary part of the matrix has to be related to the square of the matrix. So I'll show you in much more detail why that matters. But the point is this equation has to hold if your model obeys unitary time evolution. So the sort of strategy is simple. I call it the bootstrap because it's, like I said, it's a very child's play version of the sort of S-matrix bootstrap Cliff was talking about. So the idea is just take non-relativistic Hamiltonian with the Newton potential, compute scattering amplitudes with it, demand that those come from a Lorentz invariant S-matrix, and try to draw some conclusions. So specifically here, I'm showing just 2-to-2 scattering with the Newton potential. So if you compute this, everybody does this in school. It's just Coulomb scattering to lowest order. The S-matrix element for 2-to-2 scattering has a simple form, which is a coefficient with the masses divided by the momentum transfer squared. I put in a little regulator mu. This is it'll be 0 at the end of the day. And so this is not relativistic. You can't see my cursor. This thing on the left side of this equation is not relativistically invariant. You can see that because the letters are bold. Those are 3-dimensional vectors, not 4-dimensional space-time vectors. You can then show, the question is, okay, how do I make that something Lorentz invariant? And it's pretty easy to show that the only thing you can do is basically convert the 3 vectors to 4 vectors. So they have to become space-time vectors. So on the right-hand side, I'm talking about p mu squared, for example. Lorentz invariant, it's the only thing you can do, up to some sort of simple modifications that won't affect anything where in the limit we're going to worry about, which is where this momentum transfer goes to 0. So everything is going to follow from this sort of argument. So now you take this strategy and you analyze these Newtonian gravitational experiments. So this diagram on the left is sort of the non-relativistic calculation you would do. So I'm putting in Bob and Alice. It's actually crucial that you do this, sort of similar to Bob's story. I'm not going to show the computation, but there's a just straightforward perturbative calculation you do of the scattering amplitude, which says I take the mass, I prepare one of them somehow, I let it interact with the other mass, I do a readout on one, and do some measurement of the final state. So all these labels P and K are just the initial and final momenta. And you go forth and you compute non-relativistic quantum mechanical scattering amplitude. So then on the right-hand side, what I'm showing is just schematically the Lorentz invariant version of this, the unique Lorentz invariant version you can make up to modifications that don't matter for my argument. And there's this formula on the bottom for the scattering amplitude. So it looks, the important part is this middle term. So this is really just this same term, okay? It comes from the gravitational part of the whole experiment. There's two things on the left and right here with lambdas. These are the effects of the experimentalist. They're not super important. The reason the experimentalist is important is because what it changes is the amount of momentum that can be transferred in the middle of the experiment.
There are no photons.
I calculate them as, I think, external scalars to just write this down, but,
But the actual microphone.
It's nice to be in a theory session where people yell at each other in real time.
Yeah, but in the actual analysis of that experiment that you're talking about, right?
Yeah.
The system you are considering has no electromagnetism or any other fields other than the two particles which are non-relativistic and gravitational field. Is that correct?
Well, you have to actually measure something. So there is an external probe in real life. And that's actually important to run this argument.
So please explain that, because that's what we missed. At least I missed. Because you're drawing these diagrams, and I feel that all you have is these two particles, which are described Newtonian thing, and a gravitational interaction between them.
Yeah.
So what else is there?
These photons, that's what I'm putting in here. So what I really mean is, at the end, you've scattered the things gravitationally, and then you're going to have to read it out. So you have to interact with the probe system. Sorry, you have to probe the system with some kind of apparatus. That's what these photons schematically are, indicating.
So the probes are interacting with the particles. What are they interacting with?
With the massive particles.
Thanks.
So the solid lines are the massive particles, and this is just saying, like, I shine a laser to prepare the state, I shine a laser to read it out at the end. Cool. Oh, cool, I'm actually going quite fast, sorry. So I've got this formula, which is supposed to give me the probability amplitude for, some initial state with this P1, P2, and K, and to evolve to some final particular state. And the question is, can this be unitary? It is Lorentz invariant. That's sort of what this bootstrap thing shows. This formula down here is all a bunch of 4 vectors squared. It's nice and invariant. The question is it unitary? So let's look at unitarity. Okay, so we're going to focus on this middle term, the term with the G Newton in it. Unitarity, like I said, depends on, we're going to use it in the form of optical theorem, which is this second equation here, which says that the imaginary part of some amplitude has to be related to the squares of some other amplitudes. So we want to analyze the imaginary part of this amplitude. So in particular, you want to focus on the regime where this K twiddle, which means the momentum transfer between the two massive objects, becomes 0, or negative mu squared, where mu squared is going to go to 0 at the end of the day. Okay. So the reason the experimentalists are important is because once you put them in, K twiddle can actually go to 0. In the just pure Newton scattering, they cannot, or well, that's just the the infrared pole. So here, with totally normal external momenta, you can reach that pole where the gravitational interaction becomes light-like, and you can look at the imaginary part of that pole, and it has some form. In particular, it has a form where there's a g Newton and a lambda squared, where lambda is this sort of experimentalist photon strength. So now you want to ask, is it possible that that amplitude can be plugged into the unitarity equation and solve it? And if the core idea is that if there's no gravitational radiation, you cannot satisfy this equation. It's pretty easy to sort of go through and think what diagrams can exist. If there's no gravitational radiation, there are no set of diagrams you can put on the right-hand side of the optical theorem such that the left-hand side, this pole, will appear and be consistent. And actually, if you think a little more, what really happens is you try to propagate this initial state, which is totally benign. It's a photon and two massive particles, and you'll find that the outgoing set of states has norm less than 1. It has lost probability, and this is extraordinary. Well, we can argue how pathological that is, but in a naive way of thinking, that would be very pathological. So in a little more detail, what actually happens is the form of the imaginary part of that scattering amplitude has a very specific pole structure, and this is an ancient kind of way of thinking about things. That pole is actually given exactly by this two pair of diagrams multiplied by each other. So these diagrams are ones where I have so down there's this dashed line going out to the future, and what that dashed line represents is some kind of radiation going out to infinity, and that radiation has got exactly the same sort of coefficients and behavior as this line that I use to denote the gravitational interaction. So, what you're saying is there have to be states in the, asymptotic scattering Hilbert space. I don't have to think about local physics at all. They just have to be way out at infinity. They have to couple with g Newton strength. They have to be bosons. You can make some more arguments about exactly what you can say from this. But the core point is it would be inconsistent to have a model where you have Newtonian scattering in its full quantum glory and not have quantized radiation in the asymptotic Hilbert space. So, what does that really mean? So it means that if you see the Newtonian entanglement, you really know there's a 1/r operator. It's the normal one you would put into quantum mechanics. And now if I assume that the universe is Lorentz invariant and unitary, then you can really conclude that the experiment means you know that there has to be some gravitational radiation. Quantized gravitational radiation, quantized meaning it can be superposed and entangle stuff and all the usual things. And it's pretty bad. If you don't put that in, you will lose probability in time evolution. So just some notes, this argument is insensitive to the spin of the mediator, so it actually does not have to be a spin 2 graviton to do this. Gravity, you could imagine it was mediated by a spin 0 or 1 or whatever integer particle. So if you want to really claim it's the graviton, meaning the spin 2 graviton, you have to be a little more careful. And it's totally unclear, really, what happens if you try to drop or relax these assumptions of unitarity or Lorentz invariance. But very interesting to think about how much you could extend the argument. So all the details are in this paper. And maybe just to really emphasize, I think this is essentially what Bob was arguing, a very similar argument. So it's just one where instead of using causality, I'm imposing unitarity of the S matrix, but these are tightly related assumptions. Okay, so just to end this, I want to speculate on something kind of out there. So this is unpublished work, so if anybody scoops me, I'll hunt you down. So like I said, Dyson's argument about you can't detect the graviton has a number of arguments in there, and he's very careful, being Dyson, about which arguments are robust and which aren't, and what are the limits. And so actually, if you read the whole paper, which I didn't do for 10 years, you find that there are weaker arguments in certain cases. So in particular, the argument I presented at the beginning said, I want to take LIGO and rescale it. So LIGO is a specific detector architecture, which in particular is what you would call a linear detector, or an amplitude detector. So it measures the position of something continuously. And the way it works is a lot of gravitons come through in a black hole merger wave, and they all sort of act slightly and add up coherently to make a signal that you see. So a different kind of detector you could think about is something you would call maybe an intensity detector or an absorptive detector, where, unlike LIGO, where the graviton just passes through it and leaves its signal, you could imagine something where the graviton actually has to get absorbed by the detector, and then the detector will click. So this is just showing schematically like a hydrogen atom or something where you start in the ground state, the graviton comes in, and then you go to some excited state. And then you know that you try to use it as a detector by saying, well, if the thing excites, then the graviton came through. So ignoring any issues like how would you actually do that, or what are the backgrounds, there's a really big problem, which is that the absorption cross-section of a graviton, there's different ways you can try to estimate this, but it's pretty robust, that it's going to be basically given by the geometric cross-section in Planck units. So if you actually put a number, that's 10 to the negative 65 centimeters squared. So just for people who don't think about cross-sections all the time, that's 40 orders of magnitude smaller cross-section, meaning 40 orders of magnitude less likely for the interaction to happen than proton-proton scattering. It's 25 orders smaller than state-of-the-art dark matter search. So this is an extremely rare process. So how could you possibly see one of these? The only way you're going to be able to do it is with a lot of detector and a lot of gravitons. So in Dyson's paper, what he does is he actually makes the following estimate. This is a great exercise. So he says, okay, well, where am I going to get gravitons? So I'm going to get them from the sun. Stuff is moving around in the sun. It's accelerating around, so it will bremsstrahl on gravitons. And Steve Weinberg calculated in '65, this is actually the last section of the soft graviton paper, a rate for graviton emission from bremsstrahlung in the sun. And he winds up with some answer like the sun rate, I think it's like 10 megawatts of power or something in gravitons. So it's a non-trivial amount, but not a ton. And so then Dyson says, okay, if I use that as my source for gravitons, how many can I detect? And I'm going to be, very optimistic. I'm going to assume I can use every atom on the Earth as an absorptive graviton detector. And what he finds is you're going to get 4 graviton events per lifetime of the sun. So, I've proposed some crazy experiments, but I think even for me, this is pretty out there to think about doing it this way. But on the other hand, it's nice because, this is very different from this sort of like, oh, my detector will become a black hole. This is much weaker argument. This says I have a specific detector, I use this source, it was the first one I thought of, and, I get a small number. So, it's fun to ask this question, could I actually get around this by thinking of, for example, a better source and a better detector? So I'm gonna posit a crazy idea, which is not much less crazy than this, but let me put it out there. So one thing you need is a detector that can detect single gravitons. So it's not LIGO, like I said. You need something that's actually an absorptive graviton detector. So you can imagine making an optomechanical experiment like that, and that's a cool thing to do, and I think people are thinking about it. But a fun thing to note is there's actually already a detector architecture, which is rather more exotic, that exists now, which would do this. So it uses this sort of out there effect, but let me tell you how it works. This is not my observation, this is, sorry, I should have said. So this is the observation of Nick Rod in particular, and Valerie Domche at CERN, who've been thinking about this for a while now. So what they noticed is the following thing. So there's a lot of experiments in particle physics which are looking for this thing called the axion. I'm not here to motivate or sell or tell you what the axion is, just to say it's something a lot of people are trying to find. There's a lot of experiments doing it at very different frequency ranges. And the way you look for them basically is the following thing. The axion is some particle, this little a, and it will interact with electromagnetism in a very funny way. It actually couples to E dot B. So in practice, what you do is you make a device with a large external magnetic field, as big as you can find. The axion comes in, talks to that magnetic field, and converts into a photon. That's just a simple prediction of this Lagrangian, that this process will exist. And so many people are doing this now. They put giant magnetic fields somewhere, and they put a photodetector at the end, and they look for it to click every now and then, because an axion might pass through. Okay. So it was noticed actually by Reffelt and Studulski in '88. There's a really lovely paper by these guys. that the same interaction basically happens in gravity. So there's a vertex in gravity, which is a graviton, h mu nu, couples to this electromagnetic stress tensor through the exactly normal coupling you would write down. And if you just sort of work that out a little bit, you remember that the stress tensor in electromagnetism goes like the field strength squared. The stress energy is like E squared plus B squared. So actually there's an identical process to this axion-photon conversion where oops. Now I have infinite time. So, sorry? Okay. Yeah, perfect, actually. So there's this vertex where what it would predict is there's a process where a gravitational wave or a graviton comes in, hits the external magnetic field you've set up, and converts to a photon. So you can actually try to look for single gravitons, or, well, gravitational waves in general, through just counting photons on a photodetector. And since a lot of people organize these experiments with big magnets and photodetectors, you can actually just convert them directly into sort of sensitivity curves. So the picture on the bottom is a plot of what that actually works out to numerically. So these guys, Domche, Garcia-Celli, and Rod, worked out some actual numbers, taking a bunch of axion experiments, which are, have these labels like DM radio and ADMX and all this stuff, and just converted them into strain detection sensitivities. It's worth noting that these are at much higher frequencies than, say, LIGO. These are megahertz and up, so high-frequency gravitational waves. And the strain amplitudes don't look so bad, actually. They're sort of, 10 to the negative 20-ish. So you can sort of imagine that this works to arbitrary frequency, and in particular, there are very high-frequency axion searches, which are not shown on this plot. So I'm showing a picture of one on the top, just to sort of emphasize how these experiments look. So this is this thing called CAST. It's at CERN. CAST, I don't remember what it stands for. The A is axion and S is search, I think. What it is it's a giant magnet, actually an LHC beamline magnet. So this is a 10 Tesla permanent magnet that CERN has like 1,000 of these laying around. So they just took one and they strapped it to an X-ray telescope. Very nice particle physics style experience. So this blue thing is the magnet, and then there's an X-ray detector at the bottom. So this is looking for axions. Actually, they point this at the sun, and they look for axions coming out of the sun. That's not important for what I'm going to say. What is important for what I'm going to say is if you take that thing, you think of it as a gravitational wave detector at X-ray frequencies, so super high frequency gravitons. It's got a strain sensitivity that's pretty good, about 10 to the negative 24 nominally. Can it really do that? Never been demonstrated, but that's sort of the estimate you would make. And you can ask, if I actually found a gravitational wave at X-ray frequencies this way, what would it look like? And the answer is kind of interesting. If you had a gravitational wave at that frequency that you can see at the strain sensitivity, it has to have a great many gravitons in it, much like a LIGO wave has 10 to the 30 or whatever gravitons in it. However, interestingly, the number density of those gravitons is low. It's low compared to the de Broglie wavelength of the gravitational field at that frequency. So in other words, it's not really a gravitational wave, it's sort of like a dilute gas of little gravitons. And the claim then is if you actually saw something in this detector and you knew it was a graviton, and we can ask, okay, you knew it was a gravitational signal, that would, if you believe the graviton exists, that would be a single graviton absorption event, full stop. Okay. However, two huge caveats. One is that the sources for X-ray frequency gravitons are rather exotic. They are not actually ruled out, but you're talking about very small primordial black hole mergers. That's kind of out there. The other thing is actually, if you think through the quantum optics of this, seeing a single click on a detector is actually consistent with the wave being classical and your detector just being an inefficient quantum detector. So, I don't have time to go through that, but, this is a classic result in optics. So if you already thought it was gravitons, then you saw the graviton. If you didn't already think it was gravitons, you could get into a quantum optics argument about it. But I still think it's kind of fun. So the outlook, conclusions if you want. I think everyone's here, or many of us are here, because we really believe this first bullet, which is that experiments in the not infinite future will test if Newtonian gravity can entangle things. I think the claim here is that if you do that and it works, there is some substantial evidence that that's the graviton. It's evidence conditioned on some assumptions that, although simple, are powerful, Lorentz invariance and unitarity, or maybe causality. It'd be nice to continue thinking through and see how much you can relax or test those assumptions. And then finally, just to have some fun, I think interesting to note that Dyson's paper does not totally rule out the idea you could look for individual gravitons, and it's fun to try to think of a less harebrained scheme than the one I just presented. Yeah, thanks.
Thank you, Dan. We do have a discussion session reserved. So are there any burning questions? Renata.
Yeah, so I wondered about the notion of existence of the graviton I'd like to ask you about.
Sorry, we need a mic here. Hang on. Can you ask it again?
Yes, so I was going to ask you about the notion of the existence of the graviton. So with all these Dyson type arguments, do we have a graviton electric effect, or what you mentioned, the LIGO? So, yeah, so one runs, at least in these simple arguments, against some fundamental barrier of detecting single gravitons. And then Dyson draws the conclusion, which I've always been puzzled by, and therefore quantum gravity doesn't exist. Yeah, and you seem to be implicitly making the same kind of assumptions because you're looking for loopholes. Well, it's not strictly speaking the same, but you're looking for loopholes in the argument. So, but isn't what you are talking about is really arguments for, well, it exists in an EFT sense. That means I have a calculation framework. That's seems perfectly sensible, has to obey certain principles which we think of perfectly sensible physically. You do computations. However, it doesn't seem to me fundamentally in contradiction with the fact that there might be fundamental limits that prevent us from detecting single gravitons. Yeah. So in the sense, these are good entities and operationally well defined to do my computations with, but for these fundamental reasons, which are there in gravity but not in electromagnetism, certain composite objects from these might well be physical and appear in, be measurable. So I was just wondering whether you see a fundamental contradiction there.
Yeah, I think it would be interesting philosophically if you wound up in the position that you really convince yourself you cannot detect the graviton, but you also convince yourself, for example, that all of the elements of these S-matrix calculations I'm showing are there. So you now have what roughly would amount to a theorem that says the graviton exists, and I mean that in a very operational sense. It can be radiated and so forth. But then you're also going to be claiming you can't detect one.
Well, no, but it's a similar question.
As a chaos agent, I think that's a cool outcome. But let me be clear that I mean, part of this is trying to say, I don't think Dyson actually claims that fundamentally you can't detect them. I think that's actually quite clear. So that's sort of the... No,
he doesn't exclude it, but he said if it's not possible, then quantum gravity doesn't exist. And
I mean, that's just a bunch of nonsense. I mean,
okay.
I think Dyson also is a chaos agent.
So let's move on to the next question.
Can you explain briefly why it is that in your final experiment you need such high-frequency gravitons?
Oh, yeah, thanks. So it's actually, thanks. I kind of convolved two things in this slide because I'm just trying to go fast. So you could try to do this at any frequency in principle. The reason I actually wanted to think about the high frequency ones is this second bit about the number density of the gravitons in the wave that you can detect. So now you don't have a coherent, like, many graviton state where, it's not like a condensed state. It's like a dilute gas state. And so it kind of gives you some moral sense that you're really talking about, like, individual gravitons.
Okay, just a weaker signal than
It's that the wavelength of the graviton has to be extremely short at high frequency, and so then there's like less per volume to make the same energy density.
Oh, thanks. I had a comment and a technical question, if you could go back to the slide with mu. So yeah, my general comment had to do, I think, both your talk and Bob Walt's talk, which is, I think from the amplitude's point of view, the same conclusions follow, like very generally from a bootstrap, but you can prove it for any long-range force. So in other words, unitarity together with Lorentz invariance, which would apply in the weak field limit for these, will show for Brans-Dicke or any kind of modified theory, any emission or potential that they're connected and their size is fixed. But if you could go back to your slide with mu, I had a technical question.
Which one, sorry?
The one with the propagator, and you added this mu squared piece. So yeah, my confusion slightly, even though I agree with the conclusion, maybe before this.
Oh, sorry.
Is just that we can compute this exactly, so we actually know what the expression is. And in the actual, like literally with relatively simple tools, that middle formula, I think you added that mu squared because you said it was the only Lorentz invariant thing you can add. But in the actual calculation with a graviton, there is something else there that's not mu squared, which is the off-shell energy. So I'm trying to understand if you made some big assumption here, because the actual, if you took as input the actual amplitude you compute in graviton EFT with a graviton exchange, this wouldn't be the answer.
Yeah, totally. So the answer would be just k twiddle squared minus I epsilon.
Well, plus energy squared. Yeah.
Plus energy squared.
For the full relativistic calculation, what we do is you would expand in post-Newtonian, so there'd be some local, instantaneous piece, which is Coulomb. But the rest of those leading corrections are the energy corrections, which are just post-Newtonian corrections. So that isn't mu, it's not a constant, it's actually the energies. So
the mu here is just an IR regulator I put in.
No, I know, but in the actual physical calculation, the mu ends up being something you can't take to zero. That's what I'm saying.
Got it. Okay,
I can show you in the calculation, but
yeah, I would enjoy talking about that. Yeah, so to be clear, this is just the the S-channel diagram that I'm bootstrapping.
No, I get that, but this is just the graph. You would put a de Donder propagator and an exchange, and I'm just saying that mu can't be taken to be an IR regulator in the actual calculation where this is a graviton.
I see. Okay, so but the conclusion would still follow as long as you can reach the pole there.
Yes, there is a general argument that would still prove your final statement, but I'm just worried about the technical.
Cool. Okay. Yeah. Thanks.
So I know there are other questions, but I'm going to reserve those for the discussion session.